Hello friends, welcome back to my YouTube channel Journey with Vijay Kumar Srivastava. Today our study topic is infiltration rate of soil. So let's proceed. What is infiltration? Infiltration refers to the downward entry of water into the soil. When water is applied to the surface of a soil, a part of it seeps into the soil. This movement of water through the soil surface is known as infiltration. Infiltration plays an important significant role in the runoff process by affecting the timing, distribution and magnitude of runoff. Further infiltration is the primary step in the natural groundwater recharge. As runoff is concerned, it is defined as the part of the water cycle that flows over land as surface water instead of being absorbed into groundwater or evaporating. It is the part of the precipitation, snow melt, or irrigation water that appears in uncontrolled surface streams, rivers, drains, or sewers, and it flows on the surface of water after saturation point. Infiltration is the process of water entry into the soil from rainfall or irrigation, where the percolation, which is known as soil water movement, is the process of water flow from one point to another point within the soil. The rate of infiltration is primarily controlled by the rate of soil water movement below the surface, and the soil water movement continues after an infiltration event as the infiltrated water is redistributed. Infiltration and percolation play a key role in surface runoff, groundwater recharge, evapotranspiration, soil erosion, and transport of chemicals in surface and subsurface waters. Infiltration rate is defined as a speed at which water enters into the soil, and it is also termed as water intake rate and usually measured as centimeter per hour or millimeter per hour or sometimes inches per hour. The infiltration rate is the velocity or speed at which water enters into the soil and usually measured by the depth, it may be in millimeters or centimeter or inches, of the water layer that can enter in soil in 1 hour. An infiltration rate of 15 millimeters per hour means that a water layer of 15 millimeter on the soil surface will take 1 hour to infiltrate. Soil infiltration rate is defined as the volume flux of water flowing into the profile per unit of soil surface area under any set of circumstances. Infiltration rate is the rate at which the water actually infiltrates through the soil during a storm, and it must be equal the infiltration capacity or the rainfall rate, whichever is lesser. As infiltration rate is concerned, in dry soils, water infiltrates rapidly, having more speed. This is called the initial infiltration rate. As more water replaces the air in the porous spaces, the water from the soil surface infiltrates more slowly and eventually reaches a steady rate. This is called the basic infiltration rate. The infiltration rate depends on soil texture, where the size of the soil particles and the soil structure, which is the arrangement of the soil particles, very useful way of categorizing soils from an irrigation point of view. On the basis of infiltration rate, the soils are classified in different categories. Like first one is very rapid infiltration, where the infiltration rate is more than 25.4 centimeter per hour. Next is rapid infiltration, where the rate is 12.7 to 25.4 centimeters per hour. There are some soils having moderately rapid infiltration, which ranges from 6.3 to 12.7 centimeters per hour. There are moderate infiltration rate soils where the rate varies from 2 to 6.3 centimeters per hour. Next is moderately slow infiltration rate soils where it varies from 0.5 to 2 centimeters per hour. There are some soils having low infiltration rate ranging from 0.1 to 0.5 centimeters per hour, and very slow infiltration soils where the infiltration rate is less than 0.1 centimeter per hour. Different type of soils are having the different basic infiltration rate. Like in case of sand, it is less than 30 millimeters per hour, while in case of sandy loam soils, it is ranging from 20 to 30 millimeters per hour, and in loamy soil, it is from 10 to 20 millimeters per hour. In clay loam soils, it is 5 to 10 millimeters per hour, and in clay, it is lowest, which is from 1 to 5 millimeters per hour. So it depends upon the soil texture and structure. The most common method to measure the infiltration rate is by a field test using a cylinder or ring infiltrometer. There are various factors which are affecting infiltration rate. Infiltration rate vary widely. It is dependent on the soil conditions of the land surface, like it is cracked or crusted or compacted, having the land vegetation type like soil cover, surface soil characteristics like grain size, gradation, storm characteristics like intensity, duration and magnitude of soil. After that, surface soil and water temperature and chemical properties of the soil and water are important. Broadly, the factors can be grouped in soil physical conditions, soil organic matter, soil surface conditions, and fluid characteristics. As soil physical conditions are concerned, the texture, structure, moisture content, presence or absence of swelling type of clays, soil depth, impermeable layer or crust, and clay mineralogy are important parameters which are affecting infiltration rate. The type of soil like sand, silt or clay, its texture, structure, permeability and its under drainage are the important characteristics that influence infiltration. A loose permeable sandy soil will have large infiltration capacity than a tight clay soil. A soil with good under drainage having the facility to transmit the infiltrated water downward to a groundwater storage would obviously have a high infiltration capacity. Water moves more quickly through the large pore spaces in a sandy soil than it does through the small pores of a clay soil, and especially if the clay is compacted and has little or no structure or aggregation. Depending on the amount and type of clay minerals, many clay soils develop shrinkage cracks as they dry, creating a direct conduit for water to enter the soil. These clay soils have high infiltration capacities as water moves into the shrinkage cracks, although at other times when cracks are not present, their infiltration rate is characteristically slow. Infiltration rate is generally highest when the soil is dry. As the soil becomes wet, the infiltration rate slows to the rate at which water moves through the most restrictive layer, such as compacted layer or a dense layer of dense clay. Infiltration is affected by crop and land management practices that affect surface crusting and compaction. Without the protective benefits of vegetative or residue cover, bare soils is subjected to the direct impact and erosive forces to raindrops that dislodge soil particles. Dislodged soil particles fill in and block surface pores, contributing to the development of surface crust that restricts water movement into the soil. Soil organic matter affects infiltration through its positive effect on the development of stable soil aggregates or crumbs. Highly aggregated soil has increased pore space and infiltration. Soils high in organic matter also provide good habitat for soil biota such as earthworms that through their burrowing activities increase pore space and create continuous pore linking surface to subsurface soil layers. Management that reduces soil cover, distributes continuous pore space, compact soil, or reduces soil organic matter negatively impacts infiltration. Since tillage negatively affects all of these properties, it plays an important role in a soil's infiltration rate. As surface and soil factors are concerned, the surface factors are those affect the movement of water through the air-soil interface. Cover material protects the soil surface. A bare soil leads to the formation of a surface crust under the impact of raindrops or other factors, which break down the soil structure and move soil fines into the surface or near surface pores. Once formed, a crust impedes infiltration. The bare tilted soil has higher infiltration than a crusted soil initially. However, its steady state rate approaches that of the crusted soil because a crust is developing. Also, the grass covered soil has a higher rate than a crusted soil partially because the grass protects the soil from crusting. As fluid characteristics are concerned, the turbidity of water, contamination of water, and temperature of water is also important factors. Water infiltrating into the soil will have many impurities both in solution and in suspension. The turbidity of water, especially the clay and chloride content, is an important factor. As such, suspended particles block the fine pores in the soil and reduce the infiltration capacity. Contamination of water by dissolved salts can affect the soil structure and in turn affect infiltration rate. The temperature of water is also a factor in the sense that it affects the viscosity of water, which in turn affects infiltration rate. Infiltration capacity is defined as the maximum rate at which a given soil has a given time to absorb the water, and it is designated as FC field capacity and expressed in units of centimeter per hour or millimeter per hour. Infiltration is rapid in the beginning and decreases with time as pores get filled with water and soil absorbs moisture, attaining almost a steady state, which is called infiltration capacity or basic infiltration rate. Here to study the significance of infiltration rate. Infiltration capacity of a soil influences the point at which runoff takes place. Runoff refers flow of water over land surface. In the soils with a low infiltration capacity, runoff occurs even at low rainfall intensity, and thus danger of loss of topsoil due to erosion are great. Infiltration rate also influences the choice of irrigation method and design. For sprinkler irrigation, rate of application planned in such a way that it is not higher than water intake rate, and infiltration rate also reflects the structural condition of a soil, and one has to think suitable soil management practices if infiltration rate is either very rapid or very slow. A high infiltration rate is generally desirable for plant growth and the environment, and in some cases, soils that have unrestricted water movement through their profile can contribute to environmental concerns if misapplied nutrients and chemicals reach groundwater and surface water resources via subsurface flow. There are problems associated with poor function of infiltration. When water is supplied at a rate that exceeds the soil infiltration capacity, it moves downslope is runoff on sloping land or ponds on the surface of level land. When runoff occurs on bare or poorly vegetated soil, erosion takes place. Runoff carries nutrients, chemicals, and soils with it, resulting in decreased soil productivity, off-site sedimentation of water bodies, and diminished water quality. Sedimentation decreases storage capacity of reservoirs and streams and can lead to flooding. Restricted infiltration and ponding of water on the soil surface results in poor soil aeration, which leads to poor root function and plant growth, as well as reduced nutrient availability, cycling by soil organisms. Ponding and soil saturation decreases soil strength and destroys soil structure, increases detachment of soil particles, and makes soil more erodible. On the soil surface rather than in the soil profile, ponded water is subjected to increased evaporation, which leads to decreased water available for plant growth. There are some conservation practices that leads to poor infiltration, which includes incorporating, burning, or harvesting crop residues, leaving soil bare and susceptible to erosion. Tillage methods and soil disturbance activities that disrupt surface connected pores and prevent accumulation of soil organic matter, and equipments and livestock traffic, especially on wet soils that cause compaction and reduced porosity. Compacted or impervious soil layers have reduced pore space and restricted water movement through the soil profile. We have to think about improving infiltration to improve the soil quality. Several conservation practices help maintain or improve water infiltration into soil by increasing vegetative cover, managing crop residues, and increasing soil organic matter. Generally, these practices minimize soil disturbance and compaction, protect soil from erosion, and encourage the development of good soil structure and continuous pore space. As a short-term solution to poor infiltration, surface crust can be disrupted with a rotary hoe or row cultivator, and plow plants or other compacted layers can be broken using deep tillage. Long-term solution for maintaining or improving infiltration includes practices that increases soil organic matter and aggregation and reduce soil disturbance and compaction. High residue crops such as corn and small grains, perennial sort, and cover crops protect the soil surface from erosion and increase soil organic matter. When reduced tillage methods that maintain surface cover are used to plant the following crop. Application of animal manure also helps to increase soil organic matter. Increased organic matter results in increased aggregation and improved soil structure, leading to improved infiltration rates. Conservation tillage reduce soil disturbance and reducing the number of trips across a field necessary to produce a crop help leaving continuous pore space intact and minimize the opportunity for soil compaction. There are conservation practices resulting in infiltration rate favorable to soil functions, which includes conservation crop rotation practices, growing cover crops, prescribed grazing, residue and tillage management, and waste utilization. Now we will go through measurement of infiltration. Infiltration is a very complex process which can vary temporally and spatially. Selection of measurement techniques and data analysis techniques should consider these effects, and their spatial dimensions can categorize infiltration measurement techniques. A brief introduction of infiltration measurement techniques can be described as: first one, aerial measurement and point measurement. Aerial infiltration estimation is accomplished by analysis of rainfall runoff data from a watershed. For a storm, with a single runoff peak, the procedure resembles that of the calculation of an index. The rainfall hydrograph is integrated to calculate the total rainfall volume. Likewise, the runoff hydrograph is integrated to calculate the runoff volume. The infiltration volume is obtained by subtracting runoff volume from rainfall volume. The average infiltration rate is obtained by dividing infiltration volume by rainfall duration. As a point measurement is concerned, point infiltration measurements are normally made by applying water at a specific site to a finite area and measuring the intake of the soil. There are 4 types of infiltrometers: the ponded water ring or cylinder type, the sprinkler type, the tension type, and furrow type. An infiltrometer should be chosen that replicates the system being investigated. Like example, ring infiltrometers used to determine infiltration rates for inundated soils such as flood irrigation or pond seepage. Sprinkler infiltrometers should be used where the effect of rainfall on surface conditions influences the infiltration rate. Tension infiltrometers are used to determine the infiltration rates of soil matrix in the presence of macropores, and furrow infiltrometers are used when the effect of flowing water is important, as in furrow irrigation. Now, when we have completed the study of infiltration rate of soil topic, there are important questions generally asked about infiltration rate, like why does the rate of infiltration decreases with time? What is the effect of initial moisture content of soil on the rate of infiltration? What is the influence of soil texture on the infiltration? Can the infiltration rate of water in a clay soils be improved? If so, how and what are the methods? How does the rate of infiltration affect the runoff during rainfall? Has infiltration rate any relationship with the capacity of the soil to retain water? How does the choice of irrigation methods and time can be decided on the basis of the rate of infiltration? So, we have to study the topic in deep and get the answers as well. So, this presentation was all about infiltration rate, infiltration, percolation, runoff, field capacity, basic infiltration rate, etc. Thank you very much.